Okay, the topic we are going to discuss right now, that is your materials on the basis of materials properties. This is a small topic, so it will not take much more time. Material properties, I mean elastic properties. Okay, so I told you about that as we go to the energy calculations in the previous part. I will let you know that what type of materials do we have and how to calculate the energy in those materials. So types of materials, we classify the materials into three types, right? One is your ductile, the second one is your brittle, and third one is your polymers. Okay, these are three type of materials what we have to discuss in our syllabus. The ductile materials are those materials which are, you know, which approach or which gain the limit of proportionality a bit early, right? They, but they are elastic even, and when they are elastic, once they are gone with beyond elastic limit, what happens? They will not come back to their original shape. So I'm just going to make uh, um, are the spellings correct? DE or DU in chemistry? I think ductile. Ductile. Okay. What is their property? During loading, loading is basically the process of extension. Every material will have to be tested under these two um, these three tests. There are the tests of materials. And what are those tests? One, we test it during loading, then we check it during unloading, okay, and then we check its retaining for extension, retaining of, sorry, retaining of original length, you can say, right? Now, loading is applying the deforming force, applying deforming force. Unloading is removing deforming force. Okay, unloading is removing deforming force, and retaining the length if extension equals to 0 before and after, then length is restored after this. Got it? So
Yes.
the graph which you obtain during loading, that is called your loading curve. Okay, it is basically graph of force and extension during loading. Okay, then unloading curve is basically graph during removing the deforming force. So I'm just writing during unloading. Got it? So will you remember all these points with you? These are basically the tests of material, that whether it is ductile, brittle, I mean, what does it do? So here we go. That is for ductile materials. Examples of ductile materials are all metals. Okay, they are easily shapeable, easy to shape and deshape them. And the problem with ductile materials is their loading and unloading curves do not overlap. Loading and unloading curves do not overlap. They are, I mean, separate. And very, very, very important point, that is elastic limit availed or achieved bit later. Yani, elastic limit is greater. Instead of writing in this way, we can simply say the elastic limit is more or greater. For greater force, they can withstand, they can perform elasticity, or they can behave elastically, just like your steels withstand a lot of force. So this is one of the factor you can consider. And secondly, that in elastic yani once they are permanently D-shaped, they will not come back to the original shape. So after permanent deformation, after plastic deformation, what happens? Extension is permanent, right? Yani extension is not zero when deforming force is removed. Are you getting my points?
Yes.
Okay. Now I will draw the graphs according to all these properties. That is why I have written everything here in front of you. That if you have this graph or this graph, there can be two graphs for that. One is the loading curve will be like this, its arrow will be upward. This is loading curve, and this one is unloading curve. Okay, this is what this is your ULC stands for unloading curve. Its arrow is downwards, and did you see they are not overlapping? They are not overlapping. This is your load, and this is your extension. Are you getting my point? Or let's say,
Yes.
just a second, just a second. Let me make it another way around for first graph, and then it would be changed. It is low, yeah, it is load, and this is extension. I made it just due to some reason. Don't worry. And here is just, did you see that extension is permanent? Extension is not zero when you have deformed it. Yani when you have removed the deforming force, extension is not zero. Extension is permanent. Then if I have extension graph, extension x is here and load x is here, then loading curve will be something like this. This is your loading curve, and your unloading curve will be something like this. This is your unloading curve. Again, they are not overlapping, but the problem is their extension axis is not coming back to 0, 0. So here extension is again not equal to 0. Is it clear to you? Now,
Yes.
the calculations of energies are involved here. There are three types of energies which we use to calculate energy or work done on the sample. Actually, that is work done on the sample. Work done on the sample for deformation. Okay, when you are doing some work to deform the sample, that is basically area between loading curve. Okay, area between loading curve and extension axis. Please consider my words: loading curve and extension axis. Wherever the extension axis is, you will find it and you will just calculate the area between loading curve and extension axis. Is this all clear to you? So it means this entire area, which is basically between loading curve and extension axis, that is your energy, yani work done on the sample. Is it? Do you agree?
Yes.
This one. Okay. Then, if you want to find out that what will be the energy restored. So here I'm going to shade it. So this shade is basically that will give you the energy supplied, yani work done on the sample for deformation. Then if you go back to the energy restored, restored energy is what? That is the energy which is given back by your sample during deformation, yani during unloading. Okay, are you getting my point? So, for example, when you are stretching a spring, yeah, you are compressing a spring and you are going to release it, that spring will give you some sort of energy, right? That energy will be used in terms of kinetic and everything. So, rest, energy um, released during deformation, during during unloading curve, during unloading the deformation, right? For example, you are releasing a spring. Are you getting my point? I'm just writing this just as a reference. When you are releasing a spring, releasing a compressed spring, so what will it give you? It will give you the energy during unloading, right? This energy is used for further calculation. Remember this thing. This is very, very important that this is the energy used for further calculations, not the total energy. This energy is used for further calculations like kinetic energy, etc. Okay, and what is that? How to calculate that one? And that energy is equals to area between, yeah, area under or between unloading curve and extension axis. Okay, so that area I'm going to mark it with, let's say, Z here, I mean in the graph, and energy provided by this, that is equals to, let's say, Y. I'm going to give it Y. This all is Y, right? This entire is Y from this top blue graph to green line, and this one, which is I'm going to write now, that is your Z. That is basically between what? This is that area. Are you getting my point? This is the area. Or, and this is Z here, which is basically this area till this point. Yes, yeah, yeah. Is it clear?
Yes.
And the final stroke is, this is basically y minus z. Got it? This is basically y minus z. Y minus z means that is the area between two curves. This is the energy lost, dissipated. Got it? So this is the third energy which you have to calculate. Dissipated energy, which is not being obtained back. Dissipated energy, that is energy between, yani energy lost during permanent deformation, energy lost during permanent deformation. Okay, and it is the difference of, yani it is the area between both the curves. I can simply write it. It is the area between both curves. Both curves. Loading and unloading curves. So here I'm going to mention it y minus z. Is it clear to you? Here that is y minus z. That is the
Yes.
energy which you cannot get it back. But is it clear?
Yes, clear.
Okay. The second type of material is basically your polymer. Polymers are almost same materials. I will not write so much detail in every one. It was basically the first. That's why I put everything on your notice. Now I will just draw the graph and explain on the graph. So I believe that it would help you out. Okay. In these polymers, actually there is another problem with them. They are extended very quickly, right? Just like rubbers. Yes, what are polymers? Just like your rubbers. Okay. So when you extend them, they becomes non-linear very early or very quickly, but once you remove the deforming force, what happens? They are back to their original length. So Their shape is not a regular shape. I mean, you can draw anyone, no issue. This is your loading curve, and the other one is your unloading curve. The same rules are applied for everything. The area between loading curve and unloading curve, and area between extension and so on. So you will say that it is your load and it is your extension. And if I reverse the graph, extension and load here, it will give you something like this. Oh, not so bad. Oh my. Oh yeah. It is difficult to draw. Let me draw it. Something like this. Okay? Is it clear to you? So these are
Yes.
basically your loading and unloading curves of your polymers. And the last thing is your brittle materials, like your glass. Right? The glass is a material which is which do not have any extension. It does not perform any type of extension. So this is its loading curve, and the same is its unloading curve. This one. Right, got it? This is its unloading curve. And here the important point is, this is basically the elastic limit. This is basically its limit of proportionality. This is its basically even break point or ultimate break point. Do you know, I have written everything at the top of the graph. So these all are the points. Here the glass is broken. If your even break point is here and you are going to remove the deforming force below that, your glass will not be broken. Are you getting my point? But if you just applied a little bit more force, what will happen? It will not come back to its original shape. Got it?
Yes.
Yes. So these all areas will inshallah help you out to understand the concept of deformation. I believe that. And hopefully you got it. If not, then go through these notes again and try your best. Okay, Ji?
Okay, sir.
Okay. See you then.
See you, sir. Allah Hafiz.
See you. Allah Hafiz. Allah Hafiz.